Hi everyone, welcome back to ChemHelp ASAP. Today we're going to be calculating enthalpy or calculating delta H. Now I am going to show you 3 different ways to do this. Let's get started. Our first method for calculating enthalpy of a reaction is called Hess's Law. And Hess's Law takes advantage of the fact that enthalpy is a state function. So remember, a state function means that enthalpy is not dependent on the path to the final state. As long as you reach the final state, it doesn't matter what path you take. So to calculate the enthalpy of a reaction, we know the final state, the reaction. So we can use a series of known reactions as steps to find the enthalpy of our final reaction. Now, as we use this series of steps, we first have to lay some rules down of what we can and cannot do. So here are our rules for using Hess's Law. Okay, rule number 1. If you reverse a reaction, so if you take reactants to products and make it products to reactants, you need to change the sign of its delta H. If you multiply a reaction by a whole number or a fraction, you can do either. You also need to multiply the delta H by the same number. If you have species that are on the opposite sides of the reaction arrow, those are going to add out. So you can think of those as variables on opposite sides of an equals mark. And conversely, if you have species that are on the same side of the reaction arrow, those are going to add together. Again, very much like algebraic expressions. These rules are best understood in the context of an example. So let's work an example. So here is our overall reaction that we want to calculate the enthalpy for, or the delta H for. We are given 2 steps right here. What we want to do is we want to add these steps such that they add to give us this overall reaction. And then when we add their delta H's, that will give us the change in enthalpy for our overall reaction. So as I look at my 2 steps or my 2 reactions, I notice that nitrogen monoxide is not a part of my final equation. I need those to add out, which means I need them on opposite sides of the arrow. Well, right now they're on the same side of the arrow, so they would add together. So in order to get them on the opposite sides of the arrow, I need to reverse one of these reactions. So let's reverse reaction number 1. So I'm going to cross reaction 1 out, and I'm going to write it reverse. So you can see I have taken my reactants, they are now products, and my products are now reactants. Again, per my rule number 1, I have to change the sign of the delta H. So it's no longer a negative delta H, it is now a positive delta H. Okay, this is great. I now have my nitrogen monoxides on opposite sides of the equation, but I have 2 on the product side and 1 on the reactant side. I need these to add out. Remember, it is not part of our overall reaction. So I am going to take reaction 2 and I am going to multiply it by 2. So remember, when you multiply the reaction by 2, you also have to multiply the delta H by 2 as well. Here is what happens with reaction 2. At this point, I am ready to add my 2 steps together, and hopefully that'll give me my overall reaction. Okay, so putting my 2 steps with their modifications on one on top of the other so I can see what adds out. You can see that my nitrogen monoxide adds out. They're on opposite sides of the equation. I have the same number of them. My O2s are going to add together because they are on the same side of the equation. So that is simply going to be a 1 plus a 1. So I am just going to pull down my nitrogen gas. Again, I'm going to have 2 O2s, and that's going to give me 2 nitrogen dioxide, which does give me my overall reaction. So now all I need to do to calculate my delta H for the overall reaction is just add my delta H's for my steps. So my final enthalpy for this reaction is 66.3 kilojoules. Again, because enthalpy is a state function, it doesn't matter which one you start with or what order you take them in, as long as you get to the final state. So if you and a friend are working Hesss Law problems, you might find that your steps go in slightly different orders, but as long as you're getting the same enthalpy at the end, you are totally fine. Let's work another example of Hess's Law. Okay, so here is our overall reaction, and you can see this time we have been given 3 intermediate reactions, or 3 different steps that we're going to use. So the first thing that I notice is that my N2O5 appears on the reactant side in my steps, but on the product side on my overall reaction. So the first thing I'm going to do is I'm going to reverse this second step. Remember, when you reverse a step, you must reverse the sign of the delta H. So for this reaction, instead of having a negative 76.6, this is now going to become a positive 76.6 kilojoules per mole. And let's make sure we cross out this original step too, so we don't use it again. The next thing I notice is my nitric acid, my HNO3, is going to add out with this HNO3. Again, they're on opposite sides, so that's fantastic. But I have 2 nitric acids on my reactant side and only 1 on my product side. So I'm going to take this third reaction and I'm going to multiply through by 2. Remember, as you're multiplying through by 2, multiply everything through by 2. The nice thing about multiplying this reaction by 2 is it gets rid of all of my fractions in this reaction. So now I'm left with whole numbers, which personally I just kind of like. Of course, our rule is that if we multiply the reaction by 2, we need to also multiply the delta H by 2. So that is going to give me negative 348.2 kilojoules per mole. And again, I am going to cross out this reaction 3 so I don't use it accidentally. So we're starting to get pretty close here. The last thing that I am seeing, that I am noticing, is that I have hydrogens. Those are going to need to add out because they're not in my overall reaction, but right now they're both on the reactant side. So let's also flip this reaction number 1 and let's get this hydrogen on the other side of the arrow. Remembering that when I flip this reaction, I also need to change the sign of my delta H. So again, instead of it being negative 285.8, it is now going to be positive 285.8 kilojoules per mole. So at this point, I do believe I have everything adding out that I need to add out. So let's add these reactions together and let's see what we've got. My 2 nitric acids are adding out. That's fantastic. My waters are also adding out, along with my hydrogens. Now I know that feels like they're on the same side, but they are actually on opposite sides of the arrow. My oxygens are on opposite sides of the arrows. They're not going to completely add out, but I do need to subtract 1/2 from 3, and that's going to leave some oxygen on the reactant side. So let's bring down what we have left. We have a nitrogen molecule, plus we do have some O2, but again, it's because the oxygens are on opposite sides, it's going to be 3 minus 1/2. Which is 2.5, or I'll write that in as 5/2. That's it for everything that is on the left-hand side of the arrow. Now for the right-hand side of the arrow, we just have 1 N2O5 molecule. And our delta H for this reaction, again, I am just adding up all of the delta H's for these steps. That gives me 14.2 kilojoules per mole. Now, am I finished with this problem? Well, not quite, because I haven't fully matched my overall reaction, but I'm super close, right? I've added everything out that needs to add out. The only difference between the overall reaction and the reaction that I've calculated is multiplying by 2. Well, guess what we can do? We can multiply this reaction by 2. When I multiply through by 2, I'm going to get 2 nitrogens. I'll put the states in now as well. 5 oxygens and 2 N2O5s. Now, of course, when I multiply the reaction by 2, I must also multiply the delta H by 2. So that's going to be 2 times 14.2. That gives me a delta H of 28.4 kilojoules per mole. Maybe in the path you took, you didn't have to multiply your final reaction by 2. That is perfectly fine as long as you get the final overall reaction and you end up with a delta H of 28.4. So that is one way to calculate enthalpy for a reaction. I'm going to show you another way, which actually is Hess's Law, but it's in a little bit different form. Let me show you. So for this method, we are going to use something called the heats of formation. Again, it is a modifier of Hess's Law, but it does not look like the Hess's Law that we just did. But let's first talk about what is a heat of formation. So a heat of formation is the energy required to form 1 mole of a compound from its pure elements. And the key thing here is all of the substances need to be in their standard state. Okay, so what is a standard state? Well, that does depend on what the substance is. So here are some examples of standard states for pure substances. If your substance is a gas, it needs to be at 1 atmosphere. If you have a solution, it needs to have a concentration of 1 molar, and it also needs to be at 1 atmosphere. If you're a liquid or a solid, you do need to be at 1 atmosphere, and you also need to be at 25 degrees Celsius. Now, this is not all of the standard states for all pure substances, but these are the most common ones that you're going to run into. So let me show you an example of a heat of formation for a compound. So let's look at the heat of formation for water. So to form water, we need 2 elements, hydrogen and oxygen. So you can see in this reaction right here that we have hydrogen plus oxygen gives us water. Now this is a balanced chemical equation. Everything is in their standard state, but we have a problem. This reaction has formed 2 moles of water, but our heats of formation are required to form 1 mole of a compound. This is an easy fix. What we need to do is we need to take this reaction and we just need to multiply through by 1/2. So if we multiply through by 1/2, we get this reaction right here. Now we have formed 1 mole of water, and that gives us a heat of formation of negative 286 kilojoules per 1 mole of water. So this is how we get heats of formation for compounds. What about heats of formation for elements? Well, for pure elements in their standard state, the heat of formation is defined to be 0 kilojoules per mole. So anytime you have an element in their standard state, you will see a 0 as a value for its heat of formation. All right, so that is how heats of formation work, but how again do we use them to calculate the enthalpy of a reaction? Well, we use a very simple equation. Here it is right here. Our delta H for a reaction is simply the sum of the heats of formations of our products minus the sum of the heats of formation for our reactants. And all of your heats of formation need to be multiplied by N, or the number of moles. This is the stoichiometric coefficient in front of whatever compound you are looking at. This will make a little more sense when we see it worked in an example, so let's work an example. So just keeping my equation up at the top of the screen so I know what I'm working with. Here is the reaction that we want to calculate enthalpy for. Again, we're looking to calculate delta H of reaction. And usually when we're working these problems, we are given a table. So here is a table with all the different compounds and their heats of formation. Now, this is a very small table. If you have a textbook and you look in the appendix, you'll see a very large table with lots of heats of formation, but these are the ones we need. So I want to sum the heat of formation for the products, and I want to sum the heat of formation for the reactants and subtract the 2. Let's plug some numbers in. Okay, so we're calculating our delta H of our reaction. Starting with our products, we're going to need the heat of formation for NO2, and we are going to multiply that by 4 moles because there is a 4 in front of the NO2 in our overall reaction. We have 2 products though, so we're going to add to this the heat of formation for water, and that is multiplied by 6 moles, again because there is a 6 in front of the water in our overall reaction. This term here is the sum of our products. Now we need to do the sum of our reactants. So we are going to subtract, again, another sum. So we have the heat of formation for ammonia. It is multiplied by 4 because there is a 4 here in the balanced chemical equation. plus the heat of formation for our O2, which of course is multiplied by 7 because we have a 7 here in our balanced chemical equation. Okay, so let's put our numbers in for our heats of formation. Again, we're given those in our table right here. So here is what my final calculation looks like. The most difficult thing about calculating delta H this way is keeping track of your signs, especially here when you're subtracting the sum of the reactants. Make sure you sum these reactants first before you subtract. Again, oftentimes I see students get these numbers wrong just because they haven't followed through really carefully with their algebra. So just watch that. So plugging this into our calculator, we get an enthalpy of negative 1,396 kilojoules. We're not quite finished. I have one more way to show you how to calculate delta H of a reaction. For this final way, for method 3, we are going to use bond energies. So again, what is a bond energy? This is simply the energy required to break a bond. Bond energies come in a table, just like the heats of formation. So here is a table showing a bunch of different bond energies. But be careful with your bonds. You can see this is a carbon-carbon single bond, and it has a very different energy from a carbon-carbon triple bond. So you have to understand not only what elements are bonded, but how they are bonded. Now, when you break a bond, this is going to be an endothermic process. It requires energy to be put into the system or absorbed by the system. When you are forming bonds, however, that is going to be an exothermic process because energy is going to be released by the system into the surroundings. So to calculate our delta H of reaction using bond energies, here is our equation. We're going to sum the bonds broken and we're going to subtract it by the bonds that are formed. As usual, let's see an example. So let's make water. Now, to figure out what bonds are broken and what bonds are formed, we need to have Lewis structures. Thankfully, these are pretty simple Lewis structures. Hydrogen, of course, is bonded with a single bond. I am going to draw 2 hydrogen molecules because I'm going to follow my balanced chemical equation. Oxygen bonded with a double bond. I'm not going to bother with lone pairs because I just want to see the bonds. And of course, I'm forming 2 molecules of water. So I'm going to draw 2 molecules of water. And in this case, I am not worried about molecular geometry, so you do not have to draw these bent. Again, I'm just really focused on the bonds themselves. So let's figure out first which bonds are being broken here. Well, that is going to be on my reactant side. I have 2 hydrogen bonds being broken and 1 double bond between oxygen being broken. And now for my product side, let's see which bonds are formed. Well, all these bonds are new. They're all formed. So I have all of these hydrogen-oxygen bonds right here being formed. So let's just do a little summary before we plug into our equation. So we have broken 2 hydrogen-hydrogen single bonds and 1 oxygen-oxygen double bond. And we have formed 4 hydrogen-oxygen single bonds. This is going to help us pull out what bond energy we want from our table here on the right. Now we're ready to plug into our equation. So for my bonds broken, you can see here are my 2 hydrogen-hydrogen single bonds, again taken from this table right here, and my 1 oxygen-oxygen double bond here, that one was right here, minus my bonds formed. Well, my bonds formed are my 4 hydrogen-oxygen single bonds, again, energy taken from the table right here. Just like when using heats of formation, just watch your algebra with this. When we plug this into our calculator, we get a delta H of negative 509 kilojoules per mole. And those are your 3 methods for calculating enthalpy of a reaction. We have Hess's Law, we have the heats of formation, and we have bond energies. I hope you found this video helpful, and thanks so much for watching.